So we did a bunch of stuff with continuity and reviewed yesterday. So we had continuous. We looked at 2 ways to think about continuous. I think it's best if you use the 3 conditions. If you think about the 2 coming from both sides on some of your problems, what's going to be the problem with that? If you look at the precise theorem in the book, it's not that they're just equal from both sides. That just tells you the limit exists. What else has to be true? Is that the limit from the right has to equal f of that value, and the limit from the left has to equal f of that value, and they have to equal them. Yeah, it's like there's a lot of equals in there. So I prefer just the 3 conditions. I think you're safer with that one. Okay, but you can use whichever one you like. Okay, I think it's easier to mix that one up with the limit itself if you use the 2-sided thing. All right, so we're going to look at our first. Well, we did the squeeze theorem. That was pretty big. Squeeze theorem probably won't come up on the test much, though. This theorem will. I'm sure it will come up somewhere, maybe in some small way, maybe in a big way. It depends what they do per year. This is like one of our big 5 calculus theorems for the year. It's not the most exciting one by any means. It's pretty obvious what it says. But it is a big theorem. And I think this is one of the things that people find trickiest on the AP exam, these 5 theorems, working with them. And usually they don't ask that many questions about them, but if you can get a couple of those questions, you're much more prepared to get a 5. So we might as well try, okay? And this kind of stuff is used like a lot more in any type of college calculus that you would take. Okay, so the intermediate value theorem says this. So let's write down what it says and then draw the picture. So it says if f is continuous, there's a hypothesis, it's got to be continuous. Let's talk about where it's continuous. So it's continuous on the closed interval. Let's just pick some closed interval, a to b, any closed interval. And k is a number, let's put any number. Any number between f of a and f of b. So k is an x or a y value.
No, it's an x. It's an x because you put it in.
It's between these 2, and what are these 2?
Those are x's.
Y values.
Y's.
So k is a y value. It's on the y-axis, right? It says if that's true, here's the punchline, then there is at least, could be more than one, but there's at least one number, we'll call it C. That C is in the interval, so it's between A and B. And what's special about C is that f of C is equal to k. This is saying, it sounds hard, right? This is saying something really intuitive. Watch, when we draw the picture, here's what it's saying. So let's draw a case where you could use this theorem. And you use this all the time. Except it's necessary to prove a lot of advanced things.
Just saying that k is the y that you get when you plug c into the function.
Yeah, exactly. But let's look. Okay, so let's just draw some kind of function. Doesn't really matter. What does matter is that in the neighborhood we're discussing, it is continuous. That's really key. That's the whole key to this, right? If it's not continuous, something else, this might not work. So we'll see that. I'll show you a picture like that too. So let's pick an interval somewhere in there. It doesn't really matter. Let's go from, I don't know. I'm going to make this less curved. Make it easier on you guys. Let's go like this. Doesn't matter, but easier to see this way. So let's say, let's start there. There's the, okay. So we got that it's continuous, and it says, and k is any number between f of a and f of b. Let's just find f of a and f of b on our picture. There's f of a, there's f of b, right? It says if k is any number between them. K could be anything in here. You guys have the choice to pick it. I say, okay, you pick any number that's between those values. Put it there, for instance. What's the theorem guarantee?
But there's going
F
to
of
be
C
a
equals
C
K.
that equals.
Which means you can trace over to the edge and trace it down, and there's some C between here such that when you put C in, you get K.
So is this similar to the epsilon delta?
Yeah, it is. It's that kind of thinking. It's all analysis
If you
thinking.
put in, oh, that make
All this really says is that if the graph's connected, any y value on the function, you can find an x value to produce that y value. Okay, that's all the intermediate value theorem says. Why is it important? Well, can you always do this for any function?
No,
Only
if
if
it's
it's
not
continuous.
continuous, then
So let's draw something that's not continuous and
Like if
see
there
where
was
this
a
might not
hole.
work. I'm going to draw a jump. So we could draw a hole, you're right, Austin. I'm going to draw a jump, though. I think it's more blatantly obvious for that. So let's draw a function that goes like this. It's a function. Satisfies the vertical line test, right? The thing it doesn't satisfy is it doesn't satisfy it's continuous. So now if you pick an interval, so let's pick A to B, I'm just going to pick this one. Okay? And I tried to use the theorem, so I tried to pick a K between those two values. Between what two values? I got to trace over it. Right, I got to trace over and find those. So f of A is right here. F of B is up there. If I was to attempt to find the theorem, why is this not going to work? Can you see?
K won't work there. There's a big gap
Yeah,
where
you could
K
choose K in the
wouldn't
wrong
have.
place.
Will it work there?
Yeah.
It's going to work, right? Because I could trace it over and I could find a C value right here that would give me that.
But if you go
Is it going to work down here?
Yeah.
No,
Yeah,
because it's
but the theorem says it's supposed to work for K is
Right.
any number.
And it's not going to work for.
And it's not going to work for lots of K's, right? Like this K.
An infinite number of K's.
If you trace that over, you go, uh-oh. Is there any value on F that we can find that'll go up there to it? There's not. So you've got to be what? You've got to be continuous. So that's the main hypothesis that matters in this theorem. In order for you to produce y values in lots of situations, you have to be continuous. You have to have a continuous curve, a continuous function. Okay? This is really saying something quite significant. It's used all over the place. And we're going to see some theorems which go with it soon. So, where do you need this? Well, I'm going to do a proof. So here's our first higher level math proof. We're not going to see that, and AP does not emphasize proof, okay? I gave you a couple just because it really gets you thinking. But this is the first higher level math proof, and this is what I really like. I don't like geometry proofs.
Those are easy.
Stupid.
I like these.
There's so many of them.
So this is number 101 in your book. Can somebody read that out for me? Find it. It's in this assignment set. I didn't assign it.
What do you want? Which one?
Number 101 and 14.
On A, B, close A, then A that x is greater.
Okay, let's slow down.
I can write that fast, make you go.
Prove that f is continuous on
And has no zeros on.
and has no zeros. So we have how many conditions here? Yeah, two conditions. And has no zeros
On closed interval A, B,
on the closed interval, so I'm going to make it closed.
then either
Then
f of x is greater than 0 for all x,
for all x values
in closed AB,
in closed AB. You see me starting to go symbolic on you?
or f of x is less than 0.
Or f of x is less than 0. So we've got some heavy logical types of things
So
going
what is
on
that
here, which
meaning?
would be
Can
hard for you guys
walk
to
through what that
swallow.
means again?
Hold on. That means for all x values in the interval A to B
That's what I mean.
that belong to the interval A to B.
For all x in closed AB.
So symbolic notation again, this says f of x has to be bigger than 0 or positive, right? For all x values in that interval, or it has to be negative for all x values in that interval. We're supposed to prove this. Todd, yeah? Did it say that? I don't know.
Well, it has to be
Well, it
greater
has
than
No
to be
zeros,
greater
has
than
no
0, less
zeros.
than 0.
Is up there?
Yeah.
Right, it said it has no zeros, so that makes sense. Okay, so how are we going to prove this? Well, we're going to need the intermediate value theorem probably at some point, right? But that's only one part of the proof. So, here we go. Proof. This is the good stuff. Now, when you try to do a problem like this, when you try to do a proof, when I try to do these in analysis, or any of my other advanced math classes, do you think that I'm always able to just figure it out and write the proof out right line for line, and it just, okay, I write the first sentence, then I get stuck for a while. I think, and then I write the second sentence, and then I write the third
There's a lot of
sentence.
math and a lot
I have
of
lots of
things.
scratch paper, I have lots of pictures. I have to develop the ideas. I go through a couple drafts of the proof often, okay? Now I assigned you guys 2 of these. They're challenging, definitely. I only assigned you 2 though, and I won't put one of you on a test, no way. AP doesn't have these, okay? But I want you to see what they're like.
Are they 100 and 112?
Yeah. I think it was, what was it? Yeah, 100. I liked those ones. 100's actually not very bad. 112 has a sneaky trick. So, there's all kinds of ways to do proof. In geometry, you probably only proved things directly. You said if A, then B, then C, then D, then E. Oh yeah, I'm done because I got F. There are all kinds of other logical proof strategies. You can do contradiction. You can use, remember geometry had the contrapositive? Contrapositive's truth
Negate
value.
and switch.
Negate and switch. If you do that, the truth value, and you learned this in geometry if you forgot, it's the same as the original statement, so you can prove things with contrapositive.
Probably didn't learn this in geometry.
Oh, whatever, it's okay. You didn't learn contradiction. So this is another proof strategy. There's 3 big ones: direct, contradiction, and contrapositive. Those are the main 3. This one's really hard to do directly. Think about what this is really saying. Let's try to draw a picture. So that's how we're going to get started here, okay? It says, okay, prove that if f is continuous, I should have said that. If f is continuous and it has no zeros, so we got no zeros, doesn't cross the x-axis, right? No x-intercepts. And it's continuous, then one of these has to be true. I said attacking it directly is hard. Well, let's think about it. So it's continuous and has no zeros. So we got an A to B. Then either that's one of those has to be true. This is not saying something so hard. What's this look like? What's that situation look like?
It's greater than 0. It could be like a parabola that's something.
It has to be between A and B.
Yeah, well, we're just looking between A and B.
Between A and B that's greater
So
than
it's
0.
strictly greater than 0?
Well, there's the other one too that could be less than.
That's case 1. It could look something like that, right? Do I have any zeros?
Nope.
Is it continuous?
Yep.
Good. So it says it has to be either something like that or
Less than.
it has to be something like that on that interval. Does that make sense? If it's continuous and has no zeros, doesn't it have to be strictly one of those? How could it cross?
It can't.
It
It
can't.
has no zeros.
It has no zeros and it's continuous. The only other way it could cross is if it what?
Jumped.
Jumped, and we
Then
said it's
not
continuous.
so.
So does this make sense? Are we
Contradiction.
thinking this might be true?
It's a contradiction.
It's got. If this, the statement has to be true.
But the other way, like if there was a jump and there were, that's
Right, so we're going to try something sneaky to try to prove it, because this is fairly obvious that it's true. Like, if you have no
Yeah.
zeros and it's continuous, it's either got to be stuck up here or it's got to be stuck down here. It can't just jump because that would violate continuity.
Yeah.
Okay? That's what it's saying. It's saying something not too bad, but attacking it directly, I tried to do it, I couldn't do it. It took me a while. This was a hard problem to do directly. So I did contradiction. So here's what I did. I said, okay, suppose that it's continuous. This is how you do a proof. You make sure you satisfy your hypotheses. So I say, suppose f is a continuous function. Am I picking a specific one? No, I'm making this completely general to all continuous functions that possibly exist in the universe. Suppose f is a continuous function with
No zeros.
no zeros, okay, on A to B, right? So we're really just worried about A to B. If there's a zero out here somewhere, it's okay. We're just worried about A to B. So as long as that's true, now here's where I do the contradiction part. I say, okay, suppose now there exists, there's a symbol for that, I'm not going to write it. So suppose
Is
there
it a
exists.
cool symbol? slant it up a little bit, or did you just do that?
I don't know. I'm kind of bad with my symbols.
It's like a backwards
there's some
capital
slant on it.
E.
I don't remember where it's supposed to go. It's like backwards capital E. So suppose there exists an x1 in that interval. So I'm saying, let's just pretend there is a value in that interval such that, which also has a symbol. Some people just like to write it in advanced math, ST. Such that f of x1 is greater than 0. Okay? So I said suppose that happens, and this is key, because I'm trying to negate or. The negation of or is and. So I'm saying suppose this happens, and suppose there exists another x guy, x2, he's also in AB, such that f of x2 is less than 0. Okay. So the tricky part to this proof, I think the hardest part, is understanding why this is a negation of that.
Because you're showing and instead of or.
So this one says everything for all. This says for all of those guys, they've all got to be what?
Greater than.
Greater than positive. Or they've all got to be negative. What did I do here?
You took and.
I said this guy, you get a
Greater than.
positive, but then this guy, you get a negative, so that's the negation. That's tricky. That's tricky logic, right? It is. It's tricky. So maybe I'll think about it a little bit more. Okay, I'm going to keep going here. Okay, now if that's true, what happens?
Then that is not true.
Oh, but I don't think that says it right there. You need something.
Don't you have to cross if it's continuous?
Then there's.
You get a what?
You get a 0.
You get a 0. That's the next step in the proof. Okay, so if that's true, the next step in the proof says then the intermediate value theorem, here's where you need that theorem. Doesn't it say if you have two y values, one's positive and one's negative, and you have a continuous function, can't you pick any k? So we're going to pick k equals what? K equals 0. Then the intermediate value theorem demands f of x equals 0. Do you know where? No, it just says for some value. It says for some c belonging to a to b.
So
Let's draw a picture
could you
here.
have determined that this, because it doesn't have any zeros, you know it never touches that, so this theorem would.
Hold on. Give it some time. Okay. I said, okay, x1 is positive, right? Didn't I say x1 was positive? So I said x1 somewhere. I picked a random spot, okay, on a to b. So I made it positive. Let's say it's right there. Then I picked another x2, and I made it positive or negative. I made it negative, so who knows how negative, maybe down there. Doesn't the intermediate value theorem say if you're continuous between there, there's some k value right here, k, for all those spots, right? So I can pick k equals 0, and I've got to get some c value. You can see my c value right there, such that I get it. The intermediate value theorem says if you're continuous, that has to be true. Didn't we say right here? Okay. So, what's that mean? Something's bad. It's a contradiction.
So this would be not.
Thus, let's explain it a bit more. We're about on the last line. Let's go up here.
I'm gonna have to start on the next page. I can't find the right line. Even the last.
Oh, have some fun. You're
No,
finally doing
I
something
just said
super
I hate
awesome.
when I have to divide my proofs onto the next page.
Yeah, that does suck. You're right. So thus f of x would have a 0. Are we agreed? The intermediate value theorem says we can pick k equals 0 and we get a value c that will be a 0. And what's the problem with that? What do we assume right here?
You need no 0.
Yeah.
We assumed no zeros. That's a contradiction.
I'll put contradiction in big letters.
Oh yeah. You're excited. This might have taken you 2 hours. This might have taken you 10 hours.
For 10 minutes.
So you use the fancy symbol for contradiction.
That looks
You
like
earned
a
that symbol.
contradiction symbol.
Wait, what is weird X?
That is, I have found a contradiction in logic. Okay? So, then I want to state what I wanted, right? Thus, oh, and look, it was right here. Fortuitous. So thus, f of x has to be strictly greater than 0 for all x belonging to a to b, or that. Proof.
We were all this.
Wait.
Why?
So I think this really demonstrates, maybe for the first time in your mathematical career, when you have these theorems and stuff, it's not like someone just came along and said, okay, I think this is kind of the way the picture works, this is kind of the way the function works, this is kind of the way this works. Someone went through with rigorous logic and said, there is absolutely no doubt this is the way it works. So the intermediate value theorem was the clencher here. You needed it for this problem, and you'll need it for the two proofs I gave you as well. Okay? There we go. Oh yeah. We're tired, our brain's hurting, that's good.
Doing my homework Friday morning.
I just want to do draw